Well, welcome back to our course on system engineering. In this chapter, we're going to be talking about systems architecture, and that's referring to our textbook. This is chapter 9. And just to once again give context as we're progressing through this section on concept development, this is where we look at how the system architecture fits in. We do needs analysis, we do requirements analysis, functional analysis, then we do evaluation and the selection. And now we're thinking about the larger picture and how we capture the overall capability into an architecture. So let's go ahead and get into, first of all, doing an introduction to architecture. So when we think of the word architecture, for many people, architecture refers to buildings, and an architect is someone who designs buildings. Over 2 decades ago, though, a professor at the University of Southern California, USC, changed that notion. He reasoned that as systems grew in complexity, the top-level design, or more accurately, the conceptual design of the system as defined at that time, was insufficient to guide engineers and designers to accurately and efficiently do the design. He looked to the field of architecture to understand how complex systems, that is, buildings, could be created and developed, and as far as we understand, coined the term, quote, systems architecting. That was Eberhard Rechten. Architecture is associated with structures, their relationships, and expectations for their design. This applies to complex systems such as aircraft, power plants, and spacecraft as much as buildings. Therefore, Rechten's premise was to apply the principles from the field of architecture to system engineering, not as a replacement, but as a part of the development of a system. So Dr. Rechten defined the term system architecting in this way. The essence of architecting is structuring. Structuring can mean bringing form to function, bringing order out of chaos, or converting the partially formed ideas of a client into a workable conceptual model. The key techniques are balancing the needs, fitting the interfaces, and compromising among those extremes. Read closely, the principles of concept development and definition are within his definition. Conceptual design and components of architecting were once lumped into the phrase, quote, preliminary design. That term has been replaced by the more extensive architecting. So what are the roles of system architect within system engineering? The system architect's role is to liaise with the stakeholders and the engineering team to interpret the stakeholders' vision for the system and to translate the vision into a recognizable form for the designers that will develop the system. This requires the architect to see the problem from different perspectives in order to faithfully carry out the original system vision. Typically, the architect will be heavily involved at the start of the project as the system concept is developing and maturing. The systems architect may be part of the team throughout the entire project. As teams change and designers and other organizations may enter and leave the project. Hopefully, the systems architect can remain as part of the original team and retain the corporate knowledge for the origins of the system, for indoctrination of new team members, as well as providing sufficient perspective during critical design points. Well, let's talk about the types of architecture, and over the next handful of charts, we'll get a chance to be thinking about the functional, the physical, and the allocated. And in terms of an overview, as there are numerous architectural frameworks, we will concentrate on the 3 main types of architecture that the system engineers will focus on: the functional, physical, and allocated. So throughout this section, this part of the lecture and this part of the textbook, we will use a notional example of a glucose meter that is used in the healthcare domain. So as to demonstrate the development of the three types of architecture, the glucose meter is used to calculate how much glucose is in a patient's bloodstream, allowing the patient to then determine the next course of action. So let's first of all think about the functional architecture. The functional architecture is performed mainly at the start of the system engineering project effort. It describes the function or actions that must be performed while completing the system's objective or mission. This typically will be system or solution agnostic and will rather focus on describing the verbs, for example, the functions that will describe what needs to be done. These functions may then be organized by mission phase and also separated by the responsible organization / systems / person that will be performing these functions, often called swim lanes. The linkage between the functions is often what type of information or data is being exchanged between the functions and is often a noun. These provide a graphical representation of the lines of responsibility and serve as conversation between stakeholders to ensure which organization or system would be responsible to execute these functions. As we are still in the conceptual phase, the system may be more of a system concept than an actual system. Well, let's first think about the functional architectural development. For the functional architecture development, we start with identifying the different functions that the glucose meter will perform, how it will interact with the environment, how it will interact with the patient, etc. And so we're now showing these 12 functions here in the figure as listed as we're showing in the chart. Well, just to describe these 12 very quickly, F1, we look at invert voltage, F2, apply negative voltage, F3, accept glucose solution, F4, accept negative voltage, F5, generate electrical current, F6, provide reference voltage, F7, convert current to voltage, F8, amplify the signal, F9, filter noise, F10, read voltage, F11, consult lookup table, and F12, provide the glucose reading. And then if we go to the next figure, we can provide an example of the glucose meter functional architecture of taking that and putting it into a functional flow. Okay, with that, let's move on to thinking about the physical architecture. So the physical architecture is the next phase in the next phase in the physical architecture where the actual system components and subsystems are developed. These are typically in a physical block diagram that show the actual components that make up the system. For this purpose, this is the actual system. The components may also be grouped together that make up the subsystem. The subsystems may also be grouped together to make up the system. The interfaces between the components and subsystems are the physical interfaces, such as the wiring, internet connections, Ethernet connections, or wireless connections. In the event of software components, this may be thought of as a class diagram to show the diagram structures and the different types of information exchanged between the classes. So for the physical architecture development, we focus on the physical components of the glucose meter, as well as any components that interact with the environment and the patient. The 8 components identified for the glucose meter are P1, voltage inverter, P2, strip reference electrode, P3, reference electrode, P4, test strip, P5, transimpedance amplifier, P6, operational amplifier, P7, low pass filter, and P8, user interface. And so the figure that we're showing now provides an example of the glucose meter physical architecture. Well, now let's think about the allocated architecture. This is where the functions in the physical architectures merge in order to determine if we have all of the functions and physical components properly allocated. This is a simple accounting of which functions are performed by which components within the system. An ideal allocation is one function is performed only by one component. However, in complex systems, this may not be the case, as we would have multiple components where one component may perform more than one function. There is some caution in this approach if the components fails that may cause many functions to be unable to perform. Another approach is multiple components completing the same function. In this case, it may be either a cooperative effort or a redundancy of components, for example, spares ready to perform the function in the case that the leading components fail. In the case of the cooperative effort, it is imperative that the components must complete their functions, as some of them may be time or sequence dependent in order to succeed. The main purpose of the allocated architecture is to ensure that no function is left behind, so that a component in the physical architecture must satisfy the function. Otherwise, a function is left unperformed, which may jeopardize the entire system's objective. Conversely, the allocated architecture seeks to ensure that each component is carefully employed and has some function to perform. Otherwise, the components may be useless to the entire system and may be a waste of resources. During the allocated architecture phase, we look to match up the functions to the ideal components. Ideally, there will be a one-to-one mapping, but not all of the time. The important concept is to make sure that all functions and all components are accounted for. If they are not, they must go back to either the functional or physical architecture to determine where the functions/components should be combined, modified, added, or deleted. So in the table that we're showing now, it provides the allocation of our glucose meter function and components, as well as identifying the frequency of how often the functions would be executed by the components. Then, as we bring all these things together, the figure provides a visual example of the glucose meter allocated architecture, where the functions are the light colored blocks and connections by arrows, and the physical components are labeled as the gray blocks and allocated to the functions with the dashed lines. And so the bluish ones are the quote gray ones, if you will, and the other ones are not. So we see like the clear ones are function, the bluish ones are the components, for the way I've highlighted it, colorized the diagram. Well, let's talk about architectural frameworks. Architectures are used extensively now in large, complex systems development programs. Once system architecture is requested, the architect and the team have large latitude in developing and integrating products. This initially led to architectures that were technically accurate, but diverse in their structure. In order to standardize the architecture development effort and the products associated with the architectures, many organizations developed and mandated the use of architecture frameworks. An architecture framework is a set of standards that prescribes a structured approach, products, and principles for developing system architecture. Two early frameworks that emerged were the command, control, communication, computers, intelligence, surveillance, and reconnaissance C4ISR architecture framework mandated by the US DoD, and the Open Group Architecture Framework, TOGAF, developed for the commercial organizations. Both of these early frameworks have evolved significantly and are expected to continue to evolve. The early frameworks were focused on individual systems and their architecture. Newer versions, however, have expanded into the field of enterprise architecture, a subset of enterprise engineering or enterprise systems engineering. All of the current versions, including DODAF or TOGAF, have enterprise editions of their frameworks. Well, let's just talk briefly about the larger set of architectural frameworks. So many architectural frameworks exist that can be applied to system development, even if the primary purpose is an enterprise architecting. So below here are a selected list of those architectures. There's the DoD architectural framework, DODAF, and also something that has been emerging since then is the Unified Architectural Framework, UAF. There's the Open Group Architectural Framework, TOGAF, I've already mentioned. There's the Zachman Framework, Ministry of Defense Architectural Framework, MODAF. So I'm sorry, so those are two different ones. The Federal Enterprise Architectural Framework, FEAF, the NATO Architectural Framework, the NAF, the Treasury Enterprise Architectural Framework, TEAF, Integrated Architectural Framework, IAF, and the Purdue Enterprise Reference Architectural Framework. Well, let's spend a little bit more time exploring the DODAF, the DoD architectural framework. Although by no means more important or, quote, better than any other framework, we will discuss the basic products of the DODAF to illustrate the basic components of the framework. The DoD framework, like all frameworks mentioned, is divided into a series of perspectives or viewpoints. As we're trying to show here in the figure, it depicts these viewpoints using a figure right from the DODAF description. The viewpoints can be observed in three bundles. The first of the four viewpoints that describe the overall system and its environment are capability, operational, services, and systems. The intent is to bundle. For this bundle is that the system concept development starts at the beginning with the capability viewpoints in order to define what broad capabilities a system should have. This may be a means to solicit initial stakeholders on what types of capabilities should be considered. After the capabilities are completed, the architect then moves on to develop the operational viewpoints in which different scenarios and concepts of operation areas are explored to further develop the system's role in the operational environment. After this is complete, there are different services viewpoints are derived from the operational insights, which defines the different services that may be needed from the system. Finally, the systems viewpoint may be developed after the understanding what is required from the three previous viewpoints. The second bundle consists of the underlying principles, infrastructure, and standards, all data and information and standards. The all viewpoint provides some configuration control and establishes the overall intent of the architecture. The data and information viewpoints define the types of data that would be expected to be exchanged throughout the system. Finally, the standards viewpoint catalog the different standards that may be applicable to the entire system architecture. The second bundle is portrayed sideways as it is intended to be continually applied and refined at each part of the architecture. As it progresses from the capability viewpoints down to the system viewpoints, the final bundle is the project viewpoint, which serves to provide structure in the form of project management as the system architecture is under development. Similar to the second bundle, this will be updated throughout the entire architecture development. So version 2 of the framework is easily scalable from the system level to the enterprise level, where multiple systems are under development and would be integrated into legacy system architectures. In fact, each of the three major system level architectural frameworks, DODAF, MODAF, and TOGAF, are now compatible with enterprise development efforts. Furthermore, with the addition of service viewpoints, service-oriented architectures are now possible with the DODAF. With each viewpoint, a set of views is defined. A total of 52 views are defined by DODAF, organized within three viewpoints. For each view, a variety of methods and techniques are available to represent the view. For example, one view within the operational viewpoint is the operational activity model. This view can be represented by a variety of models, such as a functional flow block diagram. Other models can be identified to represent the operational activity model, such as the IDEF0 diagram, or a combination of the diagrams. Thus, an architectural framework will typically have 3 layers of entities: a set of viewpoints that define a framework, a set of views that define each frame viewpoint, and a set of models that can represent the view. Each large system development effort must have a minimum set of architectural views. Rarely will the system architecture contain all 52 architecture views. Pertinent views are decided beforehand by the system engineer and system architect, depending on the intended communication and the appropriate stakeholders. The key to developing successful system architectures is to understand the purpose of the architecture. Although each system development effort is different, depending on the magnitude and complexity of the system, all architectures have at least one common purpose: to communicate information. Choosing which framework to use, which viewpoints within the framework, which views within the viewpoint, and which models within the view all depends on the purpose the architect is trying to achieve. DODAF version 2.0.2 emphasizes fit for purpose, which encourages the system architect to produce only the viewpoints and views that are applicable to the system development at that particular time. It does no good to generate all the views if they are neither needed nor applicable to the system. As the system architect understands and learns more about the system, then additional views may be added to the architecture. The existing frameworks define the superset of viewpoints and views that may be included within the architecture. Within each view, the framework typically suggests candidate models which can be used to represent the view. A hallmark of the current frameworks, however, is the flexibility inherent within each view. If the architect desires to use a model not included in the candidate list, he can, as long as he does not violate the overall framework constraints. For example, many of the current frameworks were initially defined using traditional structured analysis models, for example, IDEF0, FFBD, and data flow diagrams, to define their views. However, engineers familiar with the object-oriented models began to use a combination of object-oriented orientation and structured analysis to model structured analysis models to represent views. As the trend increased, the organizations responsible for the common architecture frameworks revised to available models to include object orientation models that can be represent the views. As of this publication, the Unified Architectural Framework, UAF, and this is what I've already mentioned, has been released and supplants the DODAF. It is more amenable to integration with the system modeling language models and component commercial applications, which will be talked about in the next chapter and in the next lecture. Next, we'll talk about architectural views. And so the notion of architectural views is to develop representations of a system from multiple perspectives or views to assist the stakeholders in understanding a system concept and making those valuable trade-off decisions before extensive development has occurred. While many different architecture development methods and guidelines exist today, all have a very common set of these perspectives. In general, system architecture will present 3 common views of a system, and we'll talk about them one at a time. First, the operational view. This representation is from the user's or operator's perspective. This view would include products that address operational systems, phases, scenarios, and task flows information flows from the user's perspective might also be addressed. User interfaces would also be described. Example products that might be included in this view would be operational figures or graphics, scenario descriptions, including use cases, task flow diagrams, organizational charts, and information flow diagrams. Next, there are logical views, and this is this representation is from the manager's or customer's perspective. The logical view would include products that define the system's boundaries with its environment and the functional interfaces with external systems, major component functions and behaviors, data flows, internal and external data sets, internal and external users, and internal functional interfaces. Example products for this view would be functional flow block diagrams, context diagrams, N2 diagrams, IDEF0 diagrams, data flow diagrams, and various stakeholder-specific products, including business-related products. And third, we have the physical reviews. This representation is from the designer's perspective. This view would include products that define the physical system boundary, the system physical components, and how they interface and interact together, the internal databases and data structures, the IT infrastructure of the system, and the internal IT infrastructure with which the system interfaces, and the standards in force in the development. Example products include physical block diagrams down to a fairly high level of detail, database topologies, interface control documents, or ICDs as they're called, and standards. Different architectural guidelines and standards may use different names, but all three of these perspectives are included in every architectural description. A common question from someone just introduced to the concept of a system architecture is, what is the difference between architecting and designing? A convenient method of answering the question is to delineate the uses of architecture versus a design. System architecture is used to discover and refine the operational and functional requirements, to drive the system to a specific use or purpose, to discriminate between options, to resolve make/buy decisions. A system design is used to develop system components, to build and integrate system components, to understand configuration changes as the system is modified. So the nature of these uses suggests that there is a difference between architecting and engineering. System architecting is largely focused on inductive process that focuses on functionality and behavior. Consequently, architecting deals with unmeasurable parameters and characteristics as much as and as much, if not more, than the measurable ones. The tool set is largely unquantitative and imprecise. Diagramming is a large component of the architect's tool set. Heuristic typically guide an architect's decisions rather than algorithms. Design engineers can be contrasted with architecting since it relies on deductive processes. Engineering focuses on form and physical decomposition and integration. Consequently, design engineering detail with measurable quantities, characteristics, and attributes. Thus, analytical tools derived from physical are the engineer's primary tools. Given these characteristics of the two fields, which should certainly not be considered loosely coupled, the architect tends to be active in the early phases of the system development lifecycle. The architect tends to be rather dormant during the detailed design, fabrication, and unit test phases. Integration and system testing will see the architect emerge again to ensure requirements and top-level architectures are being followed. In contrast, the design engineers actively peak during the architecture's dormant phases. What about architecting in the engineering hierarchy? With the differences between architecting and engineering, it is obvious that two activities are separate. An obvious question arises, who works for whom? Although there are exceptions, system architecting is a subset of system engineering. This is different from the role and place of traditional architect, which is typically at the top. When a new building is designed, developed, and constructed, the architect plays the primary role in the building's design and continues with the prominent role throughout the development and construction. In system development, the system engineer holds a prominent technical position. Next, we'll consider the architecture development. Systems engineers must have some knowledge of how system architectures are developed in order to effectively communicate between the different teams, stakeholders, users, designers, maintainers, etc. A brief approach that system engineers can take while developing some of the architecture types is listed below. As the stakeholders have some vision of how their intended systems will operate, the architect interfaces with them and learns on what system concepts should perform. Utilizing drawings and descriptions of the operational environment, the stakeholders can then paint a picture of what the environment looks like, what the system must do, what it must face, collaborate, combat, or overcome, and what the envisioned end state would look like after successful completion of its objective. During this description, the functional architecture starts to come to life by documenting the various functions that are being performed, both by the principal system, but also by the collaborating systems as well as the adversary systems. Stakeholders are consulted to ensure that the correct functions are being described, as well as the linkage between various functions. The architecture development continues to the physical perspective to define the actual components within the system that will perform these functions. The physical architecture will continue to be constructed as multiple components will be grouped to the subsystems and then grouped to, in turn, to form the system. This process will continue for the collaborating and adversary systems as well, possibly uncovering specific interoperability features. For example, correct data fields, data formats, periodicity. They must be resolved between different systems. The architecture development concludes after consulting between the two existing architectures products to properly allocate all functions and components. This may be an iterative exercise as the designers and functional architects require some coordination to ensure all components and functions are accounted for. If not, then a rework of the requirements, functions, or design may be necessary to solve the allocation problem. Next, let's discuss architecture traceability. After each step of the architecture development is complete, there should be some traceability between the various system engineering artifacts. Functional architecture will link to the requirements that they satisfy. Physical architecture will link to the functions that they execute. Other non-functional requirements may be identified to what part of the physical system must be evaluated. For example, safety, durability, resilience, maintainability, interoperability requirements. Eventually, all parts of the architecture may be traceable to other parts. The current commercial tool set provides this feature, so the system engineer does not have to manually create and maintain this traceability, which is fortunate in the event that the system complexity increases. Traceability is also valuable when changes are made to the architecture, design, test, or requirements. What happens when one part is changed? How much of the other parts needs to be modified to adapt to that change? To manually review each element that is affected every time a change occurs would be an extraordinary effort. Existing tool sets can automatically identify what is affected and what and often perform the modification. When a change occurs within the architecture, stakeholders can also use the traceability to show where their vision and direction has impact on the architecture development. Architects can also use the traceability to ensure that the direction is faithfully implemented while following constraints, standards, and other stakeholders and other stakeholder competing needs. It is precisely this form of traceability that would promote understanding among competing stakeholders to show how the system concept may be developed and which may promote additional cooperation. Well, let's talk about two related areas. First of all, we'll talk about architecture allocation, and then we'll have a short discussion on tool sets. In terms of architecture allocation, as mentioned before, regarding the allocation of functions to components, the architecture traceability may satisfy the allocation. In addition to automatically alerting the architect if if too many functions are levied on one component so as to avoid a single point of failure, evaluating how the allocation between functions and components may also give a sense of importance on certain functions and components in which additional resiliency to failure may be warranted. Some of the resiliency may come in the form of redundant components, ready spares, additional logics, or other means to ensure that the system continues to function when confronted with some form of degradation. Allocations can then be used to form in the form of simulation or analysis to ensure that the architecture under development can handle the various environments and threats that the system was designed to confront. And finally, let's talk about tool sets. Many commercial tool sets are available to develop architectural products. When considering the selection of the tool sets, systems engineering should consider several factors. The primary choice is the expense of the architect in order to generate the desired product for the stakeholders. The architect must be confident in their ability to produce the artifacts, promote interoperability, and evaluate the development when presented the operational environments and challenges the system would face. The next important choice is the collaboration potential within the project. If organizations within the team are using the same tool, there is likely a greater chance of communication efficiency to be gained and less chance of confusion on terminology that may be tool specific. Mutual understanding and a more robust system design should be expected if the team is working with the same tool set. Other factors to consider: tool sets may be stakeholder familiarity with the tool set, either by reputation or previous experience, where a knowledgeable stakeholder can be powerful in describing their system vision and capability. Additional features that can assist the system engineer and the system architect are exportable formats such as images or reports that describe the technical details of the architecture. Digital data exports can provide additional interoperability and understanding of the architecture. In terms of collaboration with the team, many tool sets have the ability to create an interactive website that users can walk through the architecture, but do not require the actual tool to read the product. Well, this is the last topic we'll cover in this lecture and on this chapter, and we're going to be talking about architecture validation. Validating the architecture depends on the purpose, audience, and products developed. If the architecture is intended to capture existing processes and capabilities of existing systems in order to document and educate others, then this may be relatively straightforward task, as they should be current users that are familiar with the system that can help verify that the product is accurate representation of the system. When different users of the same system come together for their critique, it may be enlightening for all parties to appreciate their peers, which may or may not be known, on how the system is being used. It is also instructional for current users as well as new stakeholders that wish to understand how the system works. If the architecture is intended to portray a future 2B system concept, this may be more of a challenge to find the right stakeholders to help validate the concept, particularly if the system is a radical departure from existing designs and missions. The system architect must seek out the right type of stakeholder that holds an open mind, is willing to accept other ideas, which may be radically different than their own, and have a sense of trust to allow the system architecture to develop and evolve to attain the future objective. Representative users should also be carefully selected, as some users will revert back to the current way of operations and may not be willing to provide sufficient critical thought to see how the future system would operate. It is important to have stakeholders and partners to keep in mind future operations, environments, threats, partnerships, and opportunities to envision a realistic future system concept for which to develop. Validation of the concept may emerge when a sufficient sampling of the population of users, maintainers, and stakeholders have been exposed to the architecture. This may be realized through exercises or limited utility experiments where future concepts are tested in a future operational environment. It is here that the architecture can be tested and evaluated on whether it holds promise in the future world or can be evaluated and discarded/modified if the results are not satisfactory. Collection of objectives, exercise data, and questions to evaluate the architecture concept may be used to determine the utility of the architecture. Okay, well, let's do a summary review of the things that we've covered in this lecture, as well as this chapter. First of all, we gave an architecture introduction. The system architect's role is to liaise between the stakeholders and the engineering team to interpret the stakeholders' vision for the system, and then to translate the vision into a recognizable form for the designers that will develop the system. This requires the architect to see the problem from the different perspectives in order to faithfully carry out the original system vision. We talked about types of architectures. There are numerous architectural frameworks. We will concentrate on the three main types of architectures that the system engineer will focus on: the functional, physical, and allocated. The functional architecture is performed mainly at the start of the systems engineering project effort. It describes the functions or actions that must be performed while completing the system's objective or mission. The next phase is the physical architecture, where the actual system components and subsystems are developed. These are typically a physical block diagram that shows the actual components that may make up the system. This is where the functions and physical architectures merge in order to determine if we have all of the functions and physical components properly allocated. This simple counting of functions is performed by which components are within the system. We then talked about architecture frameworks. An architecture framework is a set of standards that prescribes a structured approach, products, and principles for developing system architecture. Each large system development effort must have a minimum set of architectural views. The key to developing successful system architectures is to understand the purpose of the architecture. Although each system development effort is different depending on the magnitude and the complexity of the system, all architectures have at least one common purpose: to communicate information. Then, concerning architectural views, architectural frameworks define the structure and modes used to develop and present system architecture. These frameworks are meant to ensure consistency across programs and articulating the various perspectives. In general, system architecture will present three common views of a system: the operational view. this representation is from the user's or operator's perspective. The logical view, this representation is from the manager or customer's perspective. The physical view, this representation is from the designer's perspective. We also talked about architecture development, as the stakeholders have some vision of how their intended system will operate. The architect interfaces with them and learns on what the system concept should perform. The architecture development continues to the physical perspective to find the actual components within the system that will perform these functions. The architecture development concludes with consulting between the two existing architectural products to properly allocate all functions and components. In terms of architectural traceability, after each step of the architecture development is complete, there should be some traceability between the various system engineering artifacts. Functional architecture will link to the requirements that they satisfy. Physical architecture will link to the functions that they execute. Other non-functional requirements may also be identified to be part of the physical system must be evaluated. For example, safety, durability, resilience, maintainability, interoperability requirements. Eventually, all of the architecture, all parts of the architecture may be traceable to other parts. And then finally, we spoke about architecture validation. It is vital to identify the purpose of the architecture in order to properly validate. If the architecture is intended to be a future that is to be system concept, this may be more of a challenge to find the right stakeholders to help validate the concept, particularly if the system is a radical departure from existing designs and missions. If the architecture is intended to capture existing processes and capabilities in the existing system in order to document and educate others, then this may be a relatively straightforward task, as there should be current users that are familiar with the system that can help verify the product is an accurate representation of the system. Okay, well, thank you very much. That's it for this lecture.